Hi everyone, welcome to the quest for Immer-mutable data. And Immer here is the contraction of the German Immer, which stands for always, and immutable, like never. So that sounds like a contradiction, but maybe it isn't. But first of all, very important, I brought stickers. Even in 2 flavors, and now raining down. So you can grab them when there's a break or something. So over a year ago, I figured that developers are too smart. Also, they're too expensive to have them do stupid administrative tasks. I mean, if you try to order a keyboard, and you have to fill in an Excel form, probably you will be a mad developer, right? We don't like it. So, things that can be done better by computers should be done by computers. And so we are always striving for automating our tasks. So a few examples. In the past, we did manual releases, and this was a cumbersome task. And we figured, well, servers can do that as well, so we moved to continuous deployments. Also, we figured that manipulating the DOM is a tiresome task, and that having components and a virtual DOM that powers it is a way more powerful abstraction. The same holds for data flow. There we can have the same gains. Instead of manually pushing our data around our applications, we can just use transparent reactive programming and have it all working for us. And not everybody is there yet, but I think this is what you will all appreciate at some time. So what was the idea of MobX when I presented it a year ago? So say you have some data, in this case representing me. And I have some components that renders my name, and then I use React to put it into the DOM. Then from that point on, I'm no longer interested in, if I change this data, how to there we go. Thanks. So at that point, we're no longer interested in thinking about how should we propagate these changes to our DOM. How do you make sure that the right data is rendered? And so that is what MobX does. Basically, what you do is you say, this data is observable. Besides that, it's still the same. And a component, you declare it as being observer of the data. At that point, MobX will figure out what is needed to be observed. So if you then change the person's name, the component will render, but if I change the age, it won't. So it's very optimized, and you don't have to write a should component update ever to achieve that. So they've told you that the view is a function of the state. And that's true, but I'm not satisfied by that. Actually, what I want is that the view is a transformation of my state. And not just a transformation, a live transformation. If it's just a function, I'm still responsible of invoking that function. So what happened next is quite amazing. MobX became quite popular, quite to my surprise, and it even became the second most popular state management library in the recent survey on the JavaScript world. So how did people respond to MobX? Well, quite differently. So people are really enthusiastic because it's so simple and fast, both performance-wise and the speed in which you can add new features and implement. And on average, when people migrate to MobX, they usually lose about 30% of their code. So there are lots of pull requests that look like this. But other people are more concerned and say, oh, it's a lot of magic which is happening here. But well, that is the price we pay for abstraction. We see the same when we use React. I mean, we don't care how the virtual DOM works as long as the semantics are clear. And maybe we now still understand how the virtual DOM works, but that time will be gone once there will be fibers in there, and then we won't have any clue anymore how it works. But if it keeps the semantics, we don't care. A lot of people are happy about Mobix because it's unopinionated on how you structure your data, how you structure your stores, where you store stuff. But for the same reason, they might also not be happy about it because it doesn't tell you how to build applications. It just manages data flows for you. And some people are happy that it uses immutable data because it fits our mental model and it's easy to work with. Everybody is comfortable in using it. But on the other hand, people are sad because it uses immutable data. And there are very interesting mathematical properties of using immutable data. So, immutable data or mutable data? Or maybe to make it more concrete, Redux or Mobix? Or, more important question, Elsa or Anna? Now you might be wondering how this relates to the previous question. But I have two small daughters, one of 3 and one of age 5. So this is the question I hear the most. So I have to answer this one first. So Anna is a very well-controlled girl. She likes protocols, and she knows to have things in a predictable way. And what is really cool, she can freeze things in time. It's really awesome. Anna, on the other hand, she's very agile, and she loves to run through things and do things quickly. And most above all, she hates ceremony. I hope you were reading the slides, not listening to what I was telling. It doesn't make any sense. But how do you choose between those two? That's a difficult question, and I cannot answer that question, at least not from a neutral point of view. But I think the benefits of each approaches have a different weight in each project. So what actually is more interesting than answering this question is looking a bit deeper. What are the driving principles behind those two seemingly opposite approaches? So Redux is all about predictability. And how does it provide predictability? It provides transactional state. At any moment in time, you have your state, you have the actions that have been played onto that state, and so you can always reproduce and see what is going on. On the other hand, Mobix is more about finding your state in a very confined, minimal way, and try to derive as much from this as is possible. We want to be reasoning just in terms of our state and the changes that are made to it, and we don't want to be reasoning in like components, what's happening there. They should be just derived. And those principles, which is very interesting, they are not conflicting. They are just talking about another part of your data flow. So it's basically the quest for a lot of cool words. So at this point you might feel like, aren't those two opposite things? Don't they move in two directions? So last year, I showed you this demo where you can have boxes being dragged around, and Mobix makes sure that the arrows stay attached to the box because the arrows are just derived from the state. And it also had time traveling. So you could go back and go forward in time. So how did that work? Actually, it was pretty simple. It just takes the store, serializes it to some JSON object, and pushes that onto a list with all the states we have, and then we can deserialize it again to be back at the previous state. And it is because we put a Mobix auto-run around it and make sure that whenever something relevant in the state is changed, this function will run again. And you will recognize this pattern. This is the same pattern as what we did with our components. Components are a function that transform the state into components, and this serialization is just a function that transforms the state into some JSON structure. But the principle is the same. So a snapshot is basically a live transformation of our state. However, there are some problems with this. First of all, MobX, because it doesn't make any assumptions on how you structure your state, cannot provide a standardized serialization function. Maybe you are using classes, and deserializing classes is a hard problem. Also, serializing your entire state is a very expensive process. Basically, you're deep cloning all of your state. And also, it uses lots of memory, because every time you get this fresh deep clone, there's no structural sharing, so you have an entire new copy of all of your state. So it's not really feasible, this approach. However, there are solutions to this problem. First of all, what if we constrain ourselves to using trees? Serializing trees is straightforward. We know how to do that. And secondly, as I just told you, a snapshot is just a derived value from your state. And rendering a tree with structural sharing, that's a problem we already solved. That's what we did for components. If we render components and some state changes, only the components affected by this change are re-rendered, and the others are kept as is. So what if we could do the same for our JSON tree? So let's talk a bit about how MobX computed values work and what's special about them. So here is a very basic person class, and it has a full name getter, it could also be a function, and it just serializes the current state into an array. Tricky thing, of course, is that each time this getter is accessed, each time this function runs, you get a fresh array. So even although the arrays are structural equivalent, they're different arrays. So what you see is if we change the person's name, and then we lock the full name twice, it will print calculating the full name twice. And that's because we are pooling all the values through our system. However, observables work the opposite way around. They change pool-based data flow to push-based data flow. So if we have observable properties and a computed value that combines those values, and if we then change the name, at that exact moment in time, it will recompute the full name, because it notifies the full name, hey, this data has changed. But after that, if we request for the value of that full name, we get the same value back each time, because we know that the backing data of that computed value didn't change. We know that MobX knows that it can just return the same value. So what actually is happening here on a very small scale is that we have structural sharing over time. So when we take that principle and we have some class representing a to-do, we can just introduce a computed value, which gives the representation of this class as a plain JavaScript object. And the output of this function will not change unless we change some of the data that has been used inside that function. And so if we then have a to-do store which contains a collection of to-dos, and we map over those to-dos, each time this computed value is invoked, or is triggered to recompute, it will map over all the to-dos, but for most of the to-dos, all the to-dos that didn't change, it will return the same JSON object. So to put it in a picture, what's happening if we change some coordinate over here, a fresh snapshot, a fresh JSON representation will be generated. That triggers the computed value in the to-do store to rerun, but it will reuse snapshots of the other to-dos, and so on and so on. So with just using computed values, we have achieved structural sharing inside a derived value, namely our snapshot. Based on that principle, I wrote a small experimental package that leverages this concept and does this serialization in a standardized way for you. So its core concept is that you have your state is a tree of models, and each of those models is a tree in itself again. And those models are mutable, they're observable, they're rich. And at any moment in time, you can just have a very cheap snapshot of them. And so those models are created using factories. And a factory just takes an example model, an example to do, and every time you need a new instance, it just copies this object and mixes in the snapshots you provide. So this allows you to go back from snapshots to objects that have computed values, methods, and all those kind of things. So here's a factory that creates a box, and after that we can just invoke that function we get from the factory with a partial of a complete or a complete snapshot, and we get back a model instance. And the same for the store, where we can define that we want to use collections. So why are those snapshots useful? The Mobix state tree library provides three functions. One to get a snapshot, one to apply a snapshot back to an existing model instance, and also a listener to retrieve a new snapshot each time some data is changed. So with that, we can build actual time traveling, which isn't expensive CPU-wise or memory-wise. We can just attach to a model and a snapshot listener, and if we want to rewind the state, we apply it back. But what you can also do is build forms that take an to-do and doesn't change the source model until you press submit on the form. And how do you do that? Well, you just make a clone of the to-do, and then once the form is submitted, you get the snapshot of the clone and you apply it back to the original. And this way you can control perfectly at which moments in time your state is modified. And by the way, clone is a built-in function, but it just takes the factory of the model and invokes it with the snapshot of the model. And then you get a complete fresh instance in exactly the same state. Cool thing is that makes also testing very easy. So we can clone some base data, invoke an action on the clone, and then assert in the end that the internal state or the serialized state is as what we would expect it. And this integrates very nicely with Jest, which has a built-in snapshot feature, and it makes testing really trivial. So what's actually cool is that I currently don't have this demo running once, I have it running twice, and those two demos aren't synced. But what I can do is, whenever there's a new snapshot, send it over a socket to whoever is listening, and if you receive some data over the socket, just apply the snapshot we receive. If you now drag it around, we see that snapshots are sent over the sockets and the applications sync. And in the log on the bottom right, you see all the snapshots passing by. Now this might seem a bit inefficient, but that's something very cool. Because we don't have immutable data as at the core of our state, it's just a derivation, we still have observable, mutable data as our single source of truth. And the nice thing about observable, mutable data is that you can precisely see what's going on. You don't get a fresh state of the world, which is the only information you have when something happens. Now you can see exactly what changed in the state. So this means that the package supports JSON patches out of the box. And for patches, there are two functions, similar to snapshot. We can just listen to patches which are emitted when, for example, an attribute is changed, and we can apply them back to a model. So if we apply that principle to our demo, we stop listening to snapshots and instead start listening to patches. And if you then apply the patch, and we receive a message, you see that we have still the same working functionality, but now we're sending actual JSON patches across the wire, which are way smaller, and which are actually a useful way of integrating with a backend. And the nice thing about state trees is that they are a fractal structure. They are trees of trees of trees. And I can demonstrate it easily if I attach a listener for patches at 2 different points in the tree. So the first listener attaches to the root of the store, and the second one attaches to a specific box. And if I then move that box around, I get 2 patches, both with the relative path from where they were attached. So what is happening is if I change the box over here, it emits a JSON patch, but that event also bubbles up and emits some data in this parent, and that event again bubbles up. And all the events are corrected to the place where they are fired. And this doesn't work for just snapshots or patches, it also works for snapshots. And what you see here, it's a recursive structure. So it means that you can safely take the arrows collection, put it into a separate repository, put it into a separate package, test it over there, have all the actions over there, and then in your application, compose all the trees together, and then you can do the high-level stuff at the root. So far, I didn't talk about actions. You saw them. I just invoked functions on model classes. But of course, we have a problem there, because we want replayable actions. Because without replayable actions, we don't have transactional state. We have snapshots, but we don't know what happens in between the snapshots. So what if we could inverse the principle of dispatching? What if instead of dispatching some description of an action, we could just invoke a function and get this description of that action as a result? So that's how actions work. Action can be declared by just adding it to the model. They will be automatically bound, and they are marked by action. And then I can just invoke that function. Nothing exciting so far, except that the action is really straightforward, and I don't have to rebuild the entire world and able to move some coordinates. Unlike patches and snapshots, I can also listen to action events and can apply them. And actions listeners can actually use as middleware. So here's a very simple logging middleware, which just listens to the store, prints the action, and then invokes the next middleware. Of course, the last middleware being actually executing the action. And so if I then move a box, I just get a description of that action. I know which method was invoked, at which place, with its arguments. So of course, I cannot just sync patches, I can also sync actions. And this is middleware, so I have to invoke the next in the stream. So if I now drag it around, instead of patches being synced, my actual actions that are invoked are synced. Also, you can do this principle if you have forms, and I just demoed that you can do that with snapshots, but if you have multiple users editing the same data, it might be more interesting to just record the actions that were applied to a clone, and then in the end, apply those actions when the form is submitted back to the original object. And the cool thing of big state tree is because this is recursive, I can attach these listeners specifically to this to-do. So I don't know about all the actions that are happening in my application. I'm just interested in actions that are applied to this specific to-do. So I can replay actions on a very confined space in my state tree. So actions are based on the Bobek's action principle. They are transactional, and they unlock a part of the state tree for editing. So actions cannot modify any state outside their own scope, which ensures that they're replayable. For references, So far we were talking about trees, but trees have a nasty principle, and that is that they don't support references going all around. And sometimes that's fine, sometimes it isn't. So what we can do is when we assign some data, normally you would get an exception on this one because it's already part of the state tree. I'm gonna skip this part because it's time. The next part is cooler. So far, we have a minimally defined snapshotable state container with replayable actions. And a lot of things more, middleware and patches, dependency injection. So it's like we combined the best of two worlds. So to demonstrate that, here is the Redux to-do MVC application. And I can change to-dos, and I can add ones. I can play it back and forth. But actually, it's not really the Redux to-do MVC example anymore. It still has its actions, it still uses the dispatcher, it still uses Redux components like provider and connect, it still uses the Redux DevTools, but it doesn't have a Redux store, and it doesn't have any reducers. Instead of that, it has Mobix state tree factories and Mobix actions. And you might be wondering, how is that possible? Well, actually, the reason for that is we can convert the one into the other. Because Mobix state trees are transactional, we can mimic Redux stores. So what that works is basically a list of renames. So a Redux store has a getState method, which is basically our getSnapshot function. And dispatching an action is basically applying an action to the root of our model. And subscribing is basically listening to new snapshots that become available. So this is roughly what my store in the Redux to-do MVC example now looks like. It's a lot more straightforward, I think. And of course, because that works, the other way around also works. So this is the Mobix state tree demo. It doesn't have any Redux inside of it, but still, the Redux DevTools work for that. I can just use the time traveling over there, because the principles of transactional state are still preserved. So just give it a try. It's still experimental, but it might provide a nice opinionated way to build stores with Mobix. But the important message is transactional state is just a reactive transformation away. Reactive transformations are really, really powerful. And maybe so far you're like, function applications are really, really powerful. But they're like having images because you have to take them yourself in a time of cameras. We have reactive function applications. We can do really cool stuff with that. I hope that's the feeling that you will leave with. If you want to know more about Mobix itself, follow the Egghead course. You know all the essential parts in half an hour, or just follow me on Twitter. And it's time for questions. Thank you. I don't know Prout.js, but the immutable structures here are just plain JavaScript objects, like by default in Redux, but it would be no problem to just generate immutable JS, immutable objects, for example, as snapshots. Yes, proxies are very nice, and I can't wait for the moment that they have landed in all major browsers. Because, for example, there are few limitations to Mobix. So, for example, you can't, on the fly, add new observable properties to existing objects. And that is something that proxies would solve. How is Mobix related to ArcGIS? Good question. RxJS is our streams, and they're all about events. However, MobX is more about concrete, tangible data. So when, for example, time is important, or you're just reasoning about events, then RxJS is the way to go, because you can combine present and past events, you can build in delays, you can really combine events in complex ways. However, if you have like data you want to preserve a state, you want to be able to see and touch and work with individual data objects, I think MobX is the better fit. What often happens is that people combine the two. So for example, you have some input and you have some RxJS stream that bounces the values, and in the end, when there's some acceptable output, at that point you update your observable state. I assume that MobX works on top of setters and getters. MobX runs in any ES5 supporting browser. So that's basically any browser we know about, except for Internet Explorer 8. What do you think about CycleJS? I think CycleJS is really cool, and I really like the mental model. And to me, it makes lots of sense, similar to RxJS, as long as you're talking about events where time plays a role. However, to do simple updates to small pieces of data, to do updates of attributes, to me it makes more sense to use reactive observable data structures instead of combining streams over there. So that at one point in time, you can really touch the data, inspect it, and from there on, go back into the reactive world again. Did we do the full evolution circle from knockout.js, stateless, and back to observables? Yes, I think so. I think the conceptual model of knockout makes lots of sense. Same for Meteor. I think it's how we expect the world to work. We think in terms of mutable identities. That's how we people reason. And the way to prove that is that the most successful software product ever, Excel spreadsheets, they are based on this principle. Everybody understands them. You don't have to be a software engineer. You don't have to be an academic for 5 years to get that. The problem with Knockout and Meteor also in some extent is that it was unpredictable when it would run its derivations, and they weren't ordered, and you could get glitches and those kind of things. So these are the things I think MobX has solved, and I think that solves the circle back to reactive data structures.
This is our last question.
How do you manage UI state and app state? Good question. What we usually do is that most of our domain-specific state, which is specific to the application, we put that in stores so that we can test them separately without UI, and we can test all the business logic. However, there's also always some volatile data, like which tab page is currently selected, is the selection box open or not. And this kind of state makes more sense for me to just put into your component or in some store that represents your UI state.